Okay, we'll get started with the What's Up meeting. Part of the meeting. And then at 7:30, we'll have our regular speaker. So we'll do your summer sky reading recommendations, and we'll also cover some outreach basics today. So first off, our monthly members observing is coming up the weekend after next. It is usually on the new moon weekend, and it's August 22nd through 24th, where we've gotten permission to use the property, and we'll be here if the skies are clear. Also a reminder, the globe at night, go outside, take a look at whatever constellation is part of the campaign for the month during August 15th through 24th. So that starts up again in 2 nights. And go to globeatnight.org and put in how many stars you see. It's a very easy way to help to gather data on our light pollution. Also, as you know, we've been having Perseids, if anybody's been lucky enough to see that before the moons come up. And then we have a minor meteor shower coming up October 9th through 11th is the next one, the Draconids. And then every month this year in 2025 for the 35th anniversary of the Hubble, we have a NASA's Hubble Challenge, where for the Northern Hemisphere this month, we have Lagoon Nebula, Wild Duck, Eagle, Sagittarius Cluster, Ring Nebula, Trifid Nebula, and Cat's Eye. And if anybody was looking at the first slide, this is one of them. Anybody want to guess which one that is? Okay. Yeah, it's Lagoon. Of course, my Lagoon looks nothing like Hubble's, nor should it. So let me just say that. Also, just a reminder, on September 20th, the Astronomy Festival on the National Mall will have, as a feature, members of the Hubble team. So if you join us in outreach down there or just want to go down and enjoy it, know that they'll be there. Also, the Astronomical League, in concert with NASA, is doing an observing challenge each month for the August, or rather for the monthly challenge objects for Hubble. There's a new challenge from the Astronomical League. It's called Huygens Toes. And toes, because I had to go look it up, stands for transits, occultations, eclipses, and shadows. Is that right? I think it is. All right. I'll put it on something else then. Anywho, for those of us who are out in the wee hours, we can take a telescope. It'll take a telescope, probably at least an 8-inch, and some steady skies, and watch the transits. The times, let's see, August 3rd is past, but coming up next week is August 19th. Eastern Daylight Time, you want to be ready about 2 in the morning until about light. And you should be able to watch the shadow of Titan go across Saturn, which is particularly nice right now with the rings being edge on. So there is an observing challenge. This one is extra special because unlike most of the challenges versus the programs, most of the challenges, they give you a certificate. This challenge, they give you a certificate and a pin. And the only other thing you need to do other than provide your observation notes is to do something outreach related to this. So guess what? What I am doing here with you here and now is outreach. I have now hereby completed my challenge for this Titan transit, the shadow. And so what my observing information looks like, we used an 8-inch Schmidt-Cassegrain, focal length of just over 2000 f10, no filter. And we found, surprisingly, that the best details were seen with our highest magnification, 6 millimeter ultra wide colossal eyepiece. And I went out to the Sky and Telescope, you can too, to find what the position of all the moons were for that particular time that we were out there. I wanted to verify I was looking in the right place and also see what else I could see. And I noticed that in addition to Titan and Rhea, that we also saw Dione underneath the rings. So even though the seeing in Maryland ain't great, we actually did get to see 3 moons, and we did get to see the shadow transit. Now, we didn't rig up a camera or anything to it, so good old-fashioned drawing is basically what I did here. It shows the 3 moons, and you could see a very tiny gap in the rings, and then Titan and Titan's shadow, which is kind of cool because it's nighttime and you're looking at this Titan moon and this shadow, so you know where the sun must be, because like doing shadow figures on your wall at home, you can figure out where your source of light is. We're so used to seeing the sun just shine down on things. So typical things that they request that you put into your notes in order to have it qualify are the date, time, place. The seeing, actually, that was borderline good that night, so I gave it a good. I gave a little bit more information than what they require. I did an SQM reading and also noted when the moon set. In the far right corner is a piece of heavens above, just noting where in the sky Saturn was, so that I would have that from my records. But also for mid-August, we have the Astronomical League's map for the month. And right overhead, we have the summer triangle, which I've mentioned before, is Deneb, the end of this Cygnus of Swan, Vega, the bright star in Lyra, and Altair, the bright star in Aquila. Funny story, the other night I was out with binoculars and I was looking for some messy objects, and boy, every time I would sweep across the triangle, I'd run into the coat hanger. So that was kind of like an old friend. It was my best buddy for the night. Upside down coat hangers, what it was hanging in the sky. Probably still too far overhead and too close to the zenith for getting any good photography, but prove me wrong. You have M13 in the keystone of Hercules. And if you have trouble finding Hercules, I look for a bow tie. To me, it's a double or a sort of a mirror image of a keystone. So the other part of the keystone comes off to the side, even though it's not symmetrical and it's a bit bigger. We're all still watching the Northern Crown Corona Borealis for when that blaze star somewhere in this area to the left of the bright star will blow, maybe 2026, we'll see. And if you missed it, or if you were out there wondering where the radiant was for the Perseids, well, Perseus is where you look. And you could see that it was low on the horizon for this particular time of night. And of course, the best time to catch your meteors is going to be between midnight and dawn, because that's when the Earth is crashing into all of that leftover comet debris going through its orbit. Of course, the Astronomical League always has some highlights that I highly recommend that folks look at. Binocular highlights and things they point out in the sky. And in particular, one thing I point out a lot in the outreach is that with the Sagittarius and the Teapot and Scorpius being in the southern horizon and kind of high up, this area that we can't see so well when it's so humid and there's moonlight here at Bear Branch, but sometimes when it's dark and steady, we can. This is the area to look for to find all kinds of nebula, star clusters. You just can't miss just pointing a telescope in this part of the sky this time of year for some wonderful delights. I do have some copies of the August 2025 evening sky map on the table with the freebies over here that you're welcome to. The blue, which is gray on the printout, saving a little bit of toner, shows where the Milky Way is. And I usually tell folks in outreach that when you find the Northern Cross or Cygnus, Cygnus is flying the length of the Milky Way. So if you can't see the Milky Way, but you want to know where it's supposed to be, that's a good landmark for you. In particular, on this star map, I just want to point out some of the really cool objects that you can see above the teapot, which is the asterism as part of the Sagittarius constellation. You've got a number of M objects here, some real favorites of mine. The little dotted ones are globular clusters. Oh, wait a minute, M22 with the crosshairs is the globular cluster. And then you've got a variety of other objects in here. This area right here between Scorpio's tail and the teapot is where the center of our galaxy is. So it's no wonder that when we're pointed in this part of the sky, it's globular cluster season, because most of our globular clusters are rotating around our center of our galaxy and therefore visible this time of year. And of course, there's the back of the sky maps. Highly recommend if you are out and you're looking for some things to see. There's naked eye objects, of course, binoculars and telescopic. And I want to point out too that we have Paul Moose doing our August observing challenge for WASI right now. He did put out some various sky charts. I wanted to show everyone where to find these objects on the larger sky map as well, in case folks aren't as familiar with the sky. So you got number one here is pointing to the star in Cassiopeia. And then number two pointing to that star in Andromeda that he has on the listing. 3 is pointing to M8. I don't think I put his full, no, I didn't put his list in here. Meant to do that. And then these slides are typically, I think I did get them up into the groups IO, so you can find this slide and use it if you like. Then you got 4 is M33. And while this is showing it pretty low in the sky for this time, of course, as the evening goes on, it rises like everything else in the sky. So it'll be easier to see as time goes on. And then you've got the last object, the 5th one. I wish I'd written them down here, but you can find the list and all of his notes in the groups IO under the subcategory of observing and topics. So I wanted to cover a little bit of the outreach and engagement resources and how-tos that are available to us as members. Going into the Night Sky Network, when you log in, you come up to our Astronomical Society page here for WASI, and you can click on the calendar for seeing our calendar, but there's also some SOPs. So in the SOP folder, let's see if I can do this without messing up everything. Here we go. So in the SOP folder, there are a number of different documents here. If folks like to, some people like to see a video, some people prefer something to read. So to add your volunteer hours towards the outreach awards, this gives you a little run through of how to do that. You just simply click on it and it brings up the document for you. And then we've got outreach resources. This is primarily links. This is our SOP for access to Bear Branch. There's some how-to for groups. There's a link for the outreach resources. All that is there in the that folder. So let me go back to this one. There we go. So there's a good number of how-tos there. I will be brutally blunt and say that if you run into a technical issue, a bunch of us will try to help, but we're not gurus on it all. So then we have two views that are visible. We have a lot of coordinators, people who do a lot of outreach. So you got a coordinator view, and then you've got a user view, and I'm going to show you the member view and the coordinator view. The coordinator view, if you're a coordinator and you're trying to talk somebody off the ledge, just know that what you can see is a lot more than what a member can see. If you look in this lower corner here. So now you see, now you don't see it, and now you see it. So here with the coordinator view, you can see we've got 15 toolkits from Night Sky Network, but there's a caveat about that I'll explain. So in the member view, you are able to see information on who else is in our club, and it's information that club members are willingly offering here. So if a club member doesn't want their phone number or their picture or their email to show, then it's not going to. So that's a member-driven thing. But those who are making their email or other information available, you can see that on the club roster. So when you're looking at the Night Sky Network under the My Club, your member view does allow that. To report an event, let's say you did some sidewalk astronomy in your neighborhood. You're checking out your telescope, collimating it, and the moon happened to be coming up and you wanted to show it to somebody, you can report that as an event in your sidewalk, on your driveway, wherever you are. Or if you went to Milk House and you want to report that you were there for 2 hours, you can click this button and do that as well. You can see that there isn't anything here that indicates the toolkits that we have, but we'll still get to that. There's also this night sky planner that's linked across the top here, and I've put the link to it here. The night sky planner is kind of nice in that it covers what's up in the sky, some of the interesting stuff that's going on. This one happens to be from sky or earthsky.org. It'll send you to some stats. It's got some videos. It's some good stuff that's available to you as a member. But there is more too, because you'll notice too in tiny print, there's a news and resources as well. So we'll click on the news and resources, and one of the things that comes up is that there is this new dynamic sun toolkit. Now, these toolkits, they get mailed to Skip, our outreach director. So if you ever bought a package of frozen peas and you see the picture has a melted pat of butter on it, you don't get the melted pat of butter with your pack of frozen peas. It's a serving suggestion. So the toolkits that are offered by the ASP are serving suggestions. They have a lot of different things. There are a lot of links, and I'm just sort of notionally showing the links here. But you can either follow the script or you can look at what's there and decide to do what you want to do with whatever outreach event you're doing. So let's click on that for a second. So here is the news article. And They go through an awful lot. There are sun cards. You can borrow them, or you can print your own set of 13 cards. There's a banner, and Skip has that, although you can print whatever size version you want. There's a playlist. There's all kinds of pictures. There's slides. If you're a slide person, there's handouts. There's all kinds of things, including how to do some of the activities and links to videos. What you do with them is up to you at an outreach event. There's a lot of latitude. Of course, we all prefer that you keep it to science and facts and all that, but you can't go wrong using any of these materials or downloading the PDFs or watching any of the videos. So if there's a particular topic you're interested in, there's 15 toolkits to choose from. I've got bits and pieces I've been pulling back together that I got from Brenda when she was here, and Skip's got them all. If there's something that you want to borrow, that's pretty easy. It's available for the ask for anything. If you want to do something in your driveway, that's outreach. It counts. So, there's also a nice little video that I put the link here again. The slides are in the group's IO for getting started with outreach. So if you are completely new to the idea and just want to get a sense of what it's about, and you prefer to watch a video, this is the link, and I'll show you that in just a moment. But you can also go into this resources, and in the search box, you can put in a topic, or you can use the drop down of keywords, and you can see that there's all kinds of topics in here. It's not even showing the whole list. You want to do something on telescopes, extrasolar planets, which are exoplanets, the galaxy, Saturn, Mars, stars, the sun. There's a good number of things listed here to choose from to do that. And then I won't make you sit through a 4-minute video when you can click on that link yourself, which is also here, and it's in the slides. But you can see.
What was that previous box called?
The previous, oh, the search box?
Yeah, it's a search box. Okay.
Yeah, it's got topics and keywords in it.
It's item number 17.
If you go to the club news, you can get to it. You can look at it, look at the right-hand side. The right-hand side of that page has has the search bar. And it makes a liar of me. Okay. Let me go to news and resources. Here we go. When you click on news and resources, then you've got the, you can put in the title or description or topic, click on the topic, and you've got this whole list of things that you can start with. You can also pick any one of these categories, which covers the toolkits as well. You can do it by date if you happen to know when it was posted. And you can see that the Astronomical League's monthly sky chart is on this news and resources page as well. So you can download it if you didn't have it handy.
Lori?
Yeah.
Excuse me. It looks like you can get to the toolkits yourself that way.
Let's do it.
I mean, before you were saying you have to talk to Skip, right?
To get, if you wanted a physical banner.
Okay, just to get the physical, but
Right, but you can
stuff.
get to everything yourself online. So
Okay,
let's do black hole survival. Okay, so if you want the fabric and the bungee cord and ping pong ball to do the activity, then ask Skip. If you have this stuff at home and you don't want to be bothered with that and you want to make your own, go for it. And all the details on how to make it is all there. and how to use it, and they even walk through stuff, and there's scripts. There's literal scripts where audience says this, you say that. So if you prefer something prescriptive, it's there for you. If you prefer to be more off the cuff, which I tend to be, because I like to answer questions as they come up, you've got all your stuff you can study up on ahead of time. And then just be prepared for it. But activities and such, they're all here. So you can download these and see step by step exactly how they do it. And this is the to-dos and to-says. Literally scripted if that's your thing. You don't have to follow the scripts. It's even got Q&As. So there is no way that anybody can hit on a topic, read through it, and then at the end feel like they couldn't, if they really wanted to, that they couldn't do something outreach with it. These are well done and done by educator types, and are meant to instill confidence, and I believe they would. And they're actually kind of a nice read, beats video games. So I've enjoyed just kind of mindlessly going through them at times. So you can see that once you get to the YouTube for the first video, that after that, they have succeeding videos. So they've broken it up into bite-sized pieces. So you don't feel like you have to warm a seat for 30 minutes or an hour to pick up something. You can just jump to how to say, I don't know, or handling difficult questions and difficult people. You can take them out of order if you like. It's up to you, basically. So that said, one thing I would like to know from all those who are here, and also those who are on our Zoom, they can put it into the chat. For outreach and public engagement, what would you like a deeper dive on in upcoming sessions? Do you want more shorts during the What's Up? Do you want a separate Zoom session with some demos and Q&As? Do you want something else?
Are you asking us right now?
I am asking you right now.
Okay, when you say a separate Zoom session, that's for people who are remotely here, right?
So it could be any date and time that we schedule it, and you wouldn't have to leave the comfort of your home.
Oh, okay. So it could be any time, not just the set aside time.
Right.
Yeah, I think the shorts idea is a good idea on short videos that are on good topics. I think that's a wonderful idea.
So more like we just did here, do some What's Up and then do a little short overview on a section of the outreach materials.
Yeah, I mean, like those questions that were in that last search box about why doesn't the moon fall to Earth? And what if the sun were replaced by a black hole the same size? What would happen? I mean, I think some of those questions
Climate change.
were I thought those were terrific. Actually, all of them in that little segment. There were like 4 questions right there. Can you go back to that?
Sure.
Screen?
Be funny, I wanted to click on that one too.
You want to do what?
I said, I wanted to click on that one too. What would happen if?
What would happen to Earth if this?
I think all those questions are.
So use this presentation as a basis to help you answer common questions asked by the profession. So I'm going to guess this is the download galaxy full of power. It's going to take a second to download that. And so you can see it sets the stage and the context. remember doing a planetarium show on this kind of thing. I am looking for,
So to be specific, Foster, you'd like to see these questions addressed during the what's up session?
Yeah, sure.
Okay, gotcha. There's no problem.
yeah. So this is,
I really enjoy the what's up because I'm a newbie and so. I want to know what to look at.
awesome, great feedback.
I've been here a while, Lord, I think it's a good job. Really.
Okay. Good. I remember when I joined that one of the things I enjoyed a lot was Chris was doing the what's ups. And he had all kinds of topics. Some were like, I feel like I didn't complete graduate level work high enough to understand, but it was so cool. Because he would like break it down, and I see he's left the room, but break it down so that it made some sense and I could kind of follow along. And it had math. Math is our friend. So it was one of the things that I enjoyed, and I wanted to make sure we kept going, especially since doing membership. I hear from everybody, people who've been teaching astronomy and people who walk in saying, I don't know anything, but the sky is cool. And I would really personally like to make sure that it feels welcoming for everybody. So everybody gets something, because I feel like I get something from everybody. So this slide deck does not specifically, without me reading it all, cover that question of what happens if the Earth, if what would happen to Earth if the sun was replaced by a black hole. However,
Gravitationally, but
Yeah, no,
we've been getting more sunsets. and
however,
it's been pretty cold.
I would definitely say, go into this news and resources, have at it. And we can even, set aside a few minutes during the what's up doing these shorts of, hey, what did you find that was really interesting in these resources on Night Sky Network this past month? Maybe somebody will ask you that question of what happens. Like, if you can't see them, how do you know they're there? Well, that's a whole nother topic, but yeah. Okay. So that was the feedback I needed from you all, and I am always looking for feedback, as is Jack. By a show of hands, did everybody read Jack's August news that came out?
Yep.
You like that?
Yep.
Yeah, he needs that feedback and affirmation that people are reading that too, because I knew.
What you want? What turns you on?
So I knew that people were enjoying it, and he needed to know that, and that also saves us a lot of that chaotic end of meeting time stuff that was going on. So that said, I see that our Mary diners are not here yet, so I'm going to pause the recording and stop the share. And
Should folks sign this card for our speaker? We always give you the card of appreciation to the speaker after this session.
Hello, everybody. I'm Kurt. Yeah, hey. I think a lot of you have met our speaker before. And if you don't know Lou Mann, here's a little bit of his background. He is a planetary scientist with over 40 years experience supporting NASA planetary research, space missions, and space science data centers. He was a member of both Voyager and Cassini infrared instrument teams and is currently chief scientist for GAMA-1 Technologies, professor of astronomy at Marymount University, and he's also president of ARIES Scientific, which, in case you don't know, is a small not-for-profit organization dedicated to astronomy education. So even though his primary research interests have been in understanding atmospheres of planets and their moons, he's also been very heavily involved in astronomy outreach, kind of like us, and public communication. So like I was just explaining to somebody, when I called him up, I didn't put his face with his name. So when I called him up, I found out he was local. I wasn't sure about that, and so I said, well, I'm gonna come speak in person, yeah.
Recently though, he just moved.
Yeah, from Virginia, and he said, yeah, he'd like to come have dinner with us. And I said, well, let me tell you how to get there. He goes, oh, I've been there before with you guys. It's like, oh, okay. So then I saw him, like, oh, yeah, now I know who he is. But now his talk tonight is going to be about what happened in the months of July and August 1977. Two space probes were launched on a visionary mission of exploration. And those are the two Voyager spacecraft. And I think they're both, well, he'll talk about them. I think they're both still active, right? Or at least Voyager 2 is.
Yeah.
And I mean, I've had office mates who had worked on Voyager, and they were still, even though that was 30 years ago, and that was 20 years after the launch, they were still every day on the phone, you know, downloading their data and stuff. So anyway, we're really happy to have you, Dr. Mayo, and I'll turn it over to you.
Thanks so much. Is the mic?
No.
It's here, it's the whole,
You just talk.
just talk, it'll pick it up.
Yeah, it was really fortunate that I'm loco. And I'm excited to be here. Thanks to Laurie for reaching out to me and inviting me to be a member of the club. I'm excited to find out what I'm gonna say tonight.
See like the rest of this.
First of all, I'm gonna use some terms that you should be familiar with. Many of you probably already are. Planetary science terms. When we talk about space, we often have to have large yardsticks because otherwise the numbers get very large, right? If you measure distances in feet, you know, it's a large number. So in planetary science, we use the AU, right? The astronomical unit, the distance, right? And it's very similar to when we go outside the solar system, we use the light year. What's a light year?
About time it takes light to travel a year.
Distance traveled by 6,000.
Speed of light, 6 trillion miles.
No. A light year it's just like a regular year, but it's less filling, low calorie type. Right.
See, I'm not the only one who does bad dad jokes.
So I was fortunate to be a member of the Voyager infrared science team at Goddard Space Flight Center for 12 years. It was the most amazing 12 years I can imagine, the most amazing mission I can imagine. So I'm going to talk to you today about Voyager, the excitement of the program as we all experienced it, the anxiety as well, the mission itself, the science return, the challenges we had. Some of you may know of some of them, probably most of you don't know all of them. And then the successful resolutions of almost every problem that we had, which in many cases I think were miracles. So let's get started. July and August of 1977, two spacecraft were launched to explore the outer solar system. These were the two Voyager spacecraft, and they are now 48 years old. It's the best bang for the buck the American public has ever seen. They are 15.5, I just checked this morning, 15.5 billion and 13 billion miles from Earth, traveling away from Earth at about 30,000 miles per hour. And that's about 3 AU per year. Now, personally, I think without question, they are humanity's ambassadors in space now. They represent a species of explorers who want to find out what exists across beyond the next hill. And maybe getting existential for a moment, maybe kind of challenge our sense of loneliness that maybe we are it, right? The answer to that question, is there life elsewhere in the universe? Whether it's yes or no, both answers are rather chilling, I think. But here we are living on a insignificant planet, orbiting an insignificant star in a no big deal galaxy. One of perhaps now 2 trillion galaxies in the observable universe and many more outside of that. So we would like to know what's beyond observable space. We would like to answer the big questions. And so for a few moments, we entrusted these 2 spacecraft to be our eyes and our ears in the distant solar system, and ultimately to be evidence of our existence. And certainly we'll talk about the golden record and how aliens can come find us and eat us.
Well, that's a possibility, unfortunately.
I know it is. So today I'm going to try to tell you the story of Voyager, and we'll talk about all the crises and the people that made this happen, as well as the science and the mission and the hardware, and all of just the story that I think maybe takes someone who's kind of been a part of that to explain what it was really like. So I hope you get something out of that. But first, what I'd like to do is I'd like to honor a great man. This is Dr. Ed Stone, Edward Carroll Stone. He died almost exactly a year ago. And at that time, the world lost a giant in the field of planetary science. He's an internationally acclaimed physicist, longtime Voyager project scientist, and for a time, director of the NASA Jet Propulsion Laboratory in Pasadena, California. And so he passed away on June 9th, 2024 at the age of 88. Ed was instrumental in the planning and oversight of many planetary missions in planetary science, heliophysics, and earth science. And he was the face of Voyager. If you all remember, most of you are old enough to remember, the daily press conferences, the daily news shots of the latest discoveries of Voyager. And it was frequently Ed Stone kind of explaining all of these new discoveries to a world that was thirsty for its discoveries and many encounters that it had with gas giants in the outer solar system in the 70s and 80s. So his vision and leadership was really what made it work. And what you don't know is that there are 11 science teams, each one with their own instrument, each one with their own science goals, each one wanting to publish. And Ed had to coordinate each of those teams, make sure everybody got the observations they needed. They got the time on the spacecraft, they got the priority they needed. And he was an absolute wizard at doing that. So a lot of the success of the Voyager mission.
Lou,
Thanks to Ed.
quick comment. Go back to your previous slide there. So there's a date disconnect between what you that he died in 2024 versus 2020. Do you see that?
Oh, well, it was 2024.
Okay, so it was 2024.
It was a year ago. Yeah. It was in all the news. You didn't see. So let me take you back to 1965. This is Jet Propulsion Laboratory in Pasadena, and it's settled within the mountains there near Los Angeles. And in 1965, Joe Cutting was head of Advanced Project Group's study of the outer planet mission profiles at JPL. And at the time, the United States and the Soviet Union had a real competition that drove manned or human exploration. We have launched Ranger and Lunar Orbiter to the moon. They were scouting trips in preparation for the eventual moon landing. And there were flights to other planets that had some draw to them. There were struggles between the political goals of manned spaceflight, which is much more expensive, and the enormous scientific return of unmanned missions, which are, I'm saying for the record, much more cost effective. Nevertheless, the US and the Soviet Union, in fact, opened a new chapter in space competition and space exploration, and that was a race to the planets. The United States Mariner 2 reached Venus in December of '62 as a flyby mission. Outer planet missions at the time had the promise of pictures of distant worlds that we hadn't seen, or at least hadn't seen with any resolution. And we're next in line as the budgets started to climb, as these space exploration budgets started to climb. But they needed sufficient power, and of course, they needed sufficient funding. So one way you economize is you minimize fuel consumption. So that was the name of the game. And we needed to wait for the right geometry, right? Remember, this is the grand tour. And that correct geometry is called a Hohmann transfer window, or a Hohmann transfer orbit. And that would use the least amount of energy and accelerate spacecraft between two elliptical orbits. That was fairly well studied and was one way of doing it. Cutting studied intermediate gravity assists, a double transfer window that led to the Pioneer 10 and 11 missions with their gravity assists. So needing a way to minimize fuel consumption and cost, the theoretical work had been done to make an outer planet grand tour mission possible, and a quadruple planetary convergence that happens only once every 176 years just turned out for all four gas giants to be on the same side of the sun in the right positions for multiple gravity assists, and that would occur in the early 1970s. This made the grand tour possible. The scope of the grand tour fluctuated. Initially, the plan was for 4 spacecraft, but space shuttle funding was in competition, and the Pioneer program was already developed, Pioneers 10 and 11 to Jupiter and Saturn. So a 4-mission concept was rejected. But in 1972, the MJS program was approved. Who knows what MJS is? Mariner, Jupiter, Saturn. That was the name of Voyager before it launched. And they would launch during the 4 planetary alignments. But at the time, NASA had no official plans to go by 4 gas giants, only 2, Jupiter and Saturn. So the plans to go to Uranus and Neptune were not in the picture early on. In fact, all the way up to launch. So there was kind of a grassroots effort with the engineers, because they knew this was possible, to design the spacecraft to significantly outperform, as we see today, their planned lifetime. So that if going to Uranus and Neptune became possible, funding politically and so on, that they could do that. So it was kind of an organic bottom-up interest that was renewing that in the mission. So JPL insisted on having cameras on these systems. They didn't have cameras, for example, on Mariner 2. They had a radio thermoelectric power source, an RTG, which had plutonium-238 as its power source. The plutonium would give off alpha particles, converting it into thorium. The alpha particles would hit the walls of the casing would heat up, and thermocouples would grab the heat and turn it into electricity. So that's how it got power. And that's what you want to do when you're flying far from the sun. It also had a reprogrammable onboard computer. First time. Nobody had thought of that. And then, of course, the Pioneer 10 and 11 missions provided lessons learned for the eventual Voyager launch and Voyager missions. Okay, there's Voyager in the clean room at JPL. So the mission planning was given a go. Ed Stone was given the lead project scientist role. They have, let's go over this just a little bit. I'll show you a schematic that's labeled in a moment. There's a, can you see my, oops. Sorry, guys. And that's, do you have a pointer?
I do, but if you use your mouse and the people online can see where you're pointing.
Well, we'll try. Not working too well. All right. In the upper right, you can see a collection of a black instrument collection. That is the scan platform. It operates a little bit like your wrist does. Okay, so it allowed the instruments that needed to be pointed to be pointed independently of the spacecraft orientation. So on the STAD platform, you put your cameras, the narrow and wide angle ISS imaging subsystem. You put your infrared spectrometer, the ARIES instrument, and the UVS ultraviolet spectrometer, as well as your photopolarimeter. These are things that needed to be pointed. And so they could do this and not mess with the, oh, thank you. Class. This group, that's the STAD platform.
You never know what's coming out of that bag.
Up here on top, you see the communication antenna, it's X-band, S-band communication. I've lost. No. Fine. No problem, I'll do this without notes. That's for your X-band, S-band communications. We don't see this. I think this sticking out here is the RTG power source. Then there's a magnetometer boom that I think is coming out there, and radio science antenna. And then you have thrusters here for pointing.
And a couple of tires.
And a couple of times, well, you don't know. You plan for the worst. This is it's a little video of the launch. Do that. There we go. And it has sound. I hope the sound comes through. No?
This is Cape Canaveral, Vandenberg, or where? Okay.
This is Canaveral.
I think you have to turn off your speaker.
It's paused, yeah.
And then when you turn off your speaker, if you unshare, then you can, when you click on share, click a button for sound.
Technology.
Yeah, but you got to turn off your speaker, otherwise we're going to echo. Okay, all right. And then when you're in the share mode, you can click a button for the share sound.
Where's that button?
You have to unshare. Stop share, and then when you go to share, there should be a button for share sound.
Oh, okay.
And then you can share screen. Or however you're sharing.
Give that a try again. All right, one more time.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. MDS, we have ignition, we have a liftoff.
Roll program is in on time, vehicle response is normal.
TVC bus voltage look good, tank pressures look good.
Okay, MDS. Engine program was in on time, vehicle response was normal also. Very smooth flight, very, very small attitude disturbances.
What a very smooth flight so far, no problem at all.
TV tank pressures look good. Plus 40 seconds.
Solid motor chamber pressures look very good. Very smooth flight.
Very smooth flying so far, no problems at all.
Vibration levels appear to be very
Needless
low.
to say, this launch was a success. Both.
Remain
Very good so far, no problem at all.
All right, I think I've lost my notes page, but it doesn't matter. It doesn't matter. Here on the left, we see the flight path, the trajectory of both the Voyager 1 and 2 spacecraft. Actually, Voyager 2 launched first, and the reason it launched first was it was actually having problems. It was Voyager 1, and they built 3 spacecraft. so that they could be interchanged if there were problems. And about a month before launch, there were a number of subsystems that needed to be swapped out. So they swapped Voyager 1 for Voyager 2. And in fact, the RTG on Voyager 2 was swapped out as well. And that engineering Voyager spacecraft is at JPL. And one of the things I want to do before the 50th anniversary, which is coming up in 2027, is stand in front of that and get my picture taken. Anyhow, so off to Jupiter in 79. Voyager 1 went to Saturn in 1980, and at that point, the mission ended. And the reason the mission ended at that point is that they wanted to get up as close as possible to Titan to get as high spatial resolution data as possible, because Titan had an atmosphere. We saw that from the ground. Methane was discovered in the atmosphere by Gerard Kuiper. It was a fascinating world, and we wanted to get up close. So they sacrificed the rest of the mission just to get close to Titan. Voyager 2, however, went on to Uranus in 86 and Neptune in 1989. As we know, both spacecraft are still operating well past the heliopause. We'll talk about that in a minute. Okay, another video. Let's see. Can we do this?
This time it should just work when you click on it.
Well.
But you don't need to stop sharing this time. Is it this button here?
It should take me to the next slide, I think. No, there we go. Thank you.
Okay.
Okay, so this is just an animation of the launches of Voyager 1 and Voyager 2. And by the way, if you're interested in following the mission, you can go to the JPL Eyes on the Solar System program, which is a 3D immersive experience anywhere in the solar system, any mission you want to find, and any planet or any other object in the solar system. So this is just kind of illustrating how they not only got to the gas giants, but you can see the impact of the gravity assist here in just a moment. Like when the waiter says, "I'll be right with you." Okay, there it is. Voyager 1 going off. Voyager 2 accelerating. It's both still in the plane of the solar system. Eventually at Saturn, Voyager 1 goes out of the plane of the solar system. It's the geometry we needed to get close to Titan. There it goes. And then Voyager 2 goes on to Uranus and Neptune. All right, let's see if we can move on here. Okay, all right. So we touched on this a little bit, but here we are with some nice labels. There's a scan platform with the pointable instruments, the narrow and wide angle ISS cameras, the UV spectrometer, the infrared spectrometer called ARIES, infrared interferometer spectrometer. It's fine. It's not a problem.
For a quick fix.
Thank you, Laurie. The radio astronomy antennas, here's the magnetometer boom. You want your magnetometers away from the spacecraft, right? So you're not measuring the spacecraft's magnetic field. Here are the hydrazine thrusters on the side, the high gain antenna with X and S band transmission. And somewhere on here, probably on the other side, is the golden record. Okay, a blow up of the scan platform. Here's the ARIES instrument. This is what I spent over 2 decades working with, not only with its health and well-being on the mission, but also using its data to develop atmospheric models for the atmosphere of Titan. Notice that it has a golden, it's a Cassegrain telescope. It has a golden covered mirror because gold is highly reflective in the infrared. There's also a UV spectrometer up here and the 2 imaging system cameras there. By the way, they're black and white cameras with 4 filters. So if you want to take a color picture, you take it in one filter and another, and those are assembled actually back on Earth. Right now, these days, if we did it that way, it would be assembled in the spacecraft. Not so back then. And just a list of these. What you'll notice is I said 11 instruments, right? And you see 12 here. The reason is that the radio science subsystem, the communication antenna, is used to probe atmospheres by sending an active radio signal through the atmosphere when you're behind the planet. As that signal is received at Earth, as you scan down through the atmosphere, it's refracted. And the refracted nature of that signal gives you a quantity T over M, temperature over mean molecular weight. And from that, you can build atmospheric models, temperature profiles for the atmosphere. Well, the Voyager had 3 computer systems. This is the CCS. It was responsible for the kind of general coordination of signals and commands. By the way, you have more memory on your watch, these things. Yeah. The attitude articulation control system kept the spacecraft pointed and oriented. And one of its primary functions was just to make sure that the communications antenna was pointed toward Earth so that it could receive commands and send data. The flight data system has been in the news recently. Is anybody aware of that? Voyager had some problems. I forget whether it was Voyager 1 or 2, but the flight data system was, which is responsible for coordinating the formatting and coordinating the data from all the science instruments. It was sending back garbage, and so this is the miracle of these missions, that the ground people, the people at mission control, fix these things when they're billions of miles away and have a 1 day, one-way light time, right? So it's 2 days before you find out if what you've done works. They figured out what the problem was likely a cosmic ray hit in one of its memory chips. And so they were able to pull the data, the Fortran and assembler code out of that area of memory and put it somewhere else, and they got it working again. These guys work miracles.
Is that a serial number 3? Is that what SN003 is?
I think so.
Wow.
Oh, all these systems were redundant as well, and we're already on the backup. Okay, the golden record. Carl Sagan pushed pretty hard to have this put on the Voyagers, and also there were records, plaques put on the Pioneer 10 and 11 missions.
This was the plaque. This was the plaque.
It's a record.
Oh, it's a record.
Yeah. Anybody know what a record is?
He should.
It's a phonograph record. All right, let's see if I can decipher this for you. First of all, there is a radioactive, a place in the record, I forget where it is, where there's a radioactive source. And that radioactive source has a half-life of 4.5 billion years. So by ratioing the amount of the original source to its decayed material, an alien civilization could tell when this thing was launched.
Right.
Scary, but you know. All right. Here's the turntable from looking from on top. There's the cartridge. This is the speed of the turntable in binary code. And I believe that the time standard for this is the oscillations between different quantum states of the hydrogen atom. And that's what is represented here.
Right.
This is showing the signal that you're likely to get out of the phonograph. This shows how the roster would fill the screen. And then if everything's done right, if the aliens have built the right phonograph, this is the first image that they would see. This shows how to get to us. These are some number of pulsars. And you can't see it easily here, but there are binary codes that represent the frequency of the pulsar rate. So if you know that, and you know where all these pulsars are relative to Earth, in theory, you should be able to find out where we are, at least where our solar system is.
So Lou, let me just comment right there, so.
I don't accept comments.
Carl Sagan decided for the rest of us to announce where we were in the universe. And so what'll enable him to do that?
NASA signed off on it.
There you go.
Kind
And we've been sending TV programs that are way out there farther than you'll, this Pioneer will ever get, a Voyager will ever get.
That's true. In 2027, the Voyagers, both of them approximately, will be 1 light day away. All right, and the nearest star besides the sun is 4.3 light years, so I don't think we're too worried about that.
With the record, was there a political aspect of that in terms of getting public interest in unmanned missions?
I don't think so, not from Carl's point of view. He was a visionary.
Oh, I know, yeah,
And he believed very strongly, although he was a skeptic. He believed very strongly there was likely life out there beyond the Earth. This is just a picture of them demonstrating the record, and the casing will go in. And then here we see them putting the record that they're submit to one of the Voyager spacecraft. There's the RTG.
Didn't they also include a stylus or something for the record?
I don't think so. I don't think so. I could be wrong, but I don't think so. I think it's just the damn record.
what was the record made out of?
It's gold. It may have a beryllium covering. I'm forgetting, but I think that's right.
I think they put directions on how to make the player for it, didn't they? Right?
Yeah, that's what we just.
That's
I think that has. Just the direction.
Here's some-
Slides and everything.
Here's some examples of the pictures that were put on the record. Just kind of life and human daily life. There were also sounds on the record, sounds of greetings from over 100 different languages. Chuck Berry was on the record. I mean, his Rock Around the Clock or whatever that was.
Beethoven.
So just kind of trying to give aliens an idea of how we taste, I guess.
And so that tells we have bad taste, so.
The commands to the spacecraft and the data and housekeeping data came back from the spacecraft were set and received by the Deep Space Network. This is a series of 3 radio telescopes positioned around the Earth, so you can have 24/7 connectivity with your deep space mission. You still use the Deep Space Network today, of course. Every day during encounter, probably plus or minus 2 weeks from encounter of each planet, there were press conferences. Every instrument team had to be ready. 10 a.m. The von Karman auditorium was filled with the press. And so we would get up here. Robert Parks, the Voyager project manager, there's Ed Stone again, a much younger Ed Stone, and Brad Smith, who was head of the imaging science team. Of course, the imaging science team got all the press. Nobody cared about the squiggles from the UV spectrometer or the infrared spectrometer. But we had to report our findings nonetheless. Oops, sorry. There we go. So there's the von Karman auditorium. There's all of the press, everybody gathered. I mean, they were piling out the door, of course. This is the press room where they were gathering those teletypes. Gathered to send in the information they found. There's the press conference. There were a number of rooms for individual interviews from various members of the science team. This is what it was all about. We had no idea I mean, in retrospect, we had very little idea what the outer solar system was like. I have a book that my aunt and uncle sent me from the 1960s. Here's a picture of Uranus. It's kind of a dot. Here's Neptune. It's a smaller dot. Here's Pluto. It's a smaller dot. I mean, that's kind of what we knew about the outer solar system. The pictures we had, the ground, even the pioneer images of Jupiter and Saturn were not that great. So every time new information came in, was an exciting moment. People would crowd around, probably not video screens, sometimes video screens, but sometimes just paper coming out of a teletype or a printer, a line printer, to see the new discoveries that have been made that nobody else knew, nobody in the world knew, except the people crowding around the data. This is the command and control area at JPL. Looks pretty dated. Yeah, but that's what it was. I love this picture. This is Lonnie Lane. He was the head of the photopolarimeter group. And everybody crowding around him. This might be Larry Herrick, who worked on the ARIES team. And I'm not sure. Anyhow, this data here, they pointed the photopolarimeter at the rings of Saturn. And there's a star behind the ring. And as the star drifted, right, when there was no ring material, the signal would be bright. When there was ring material, the signal would be dim. And that's what this is, very high resolution of the structure of Saturn's rings. And that was the first time anyone had seen this. And it's just amazing. I mean, I'll show you some more pictures. You have people kind of crowding around, lying on floors, anything they can do to get close to these new discoveries. It was an amazing time. Let's see, I'm forgetting who that is. He's with the imaging team, however, and he's explaining the some of the images we got back from I think the moons of Saturn. And so here's what I see. Here's a woman kind of any way she can get in there. People looking over other people. I mean, it was you know, discoveries being made almost every minute as data came in, as it was analyzed. This is Linda Stilker. Linda is now, I think, now she's project manager for Voyager as the heliophysics mission. And Linda at the time was the liaison between the ARIES infrared group at Goddard and JPL. So she would come out and help us design our observing sequences, and then she'd take that back to JPL and communicate that. She was great. These days, the instrument teams kind of do that on their own and take responsibility for the command and control of their instruments. But at the time, that was all done from JPL. So Linda was the linchpin for that. And this one? There we go. Okay. So I worked with all these guys. Some of them are not with us any longer. Some of them are. This is Rudy Honnell. He's the father of planetary spectroscopy, certainly using Michelson interferometers to get high spectral resolution data from the planets. Virgil Cundy, he was the PI on the Cassini Sears infrared spectrometer and a co-I on Voyager. And we played volleyball together. And sometimes we'd go out for drinks afterwards and I'd stay just to drive him home. Mike Flazar took over as project manager for Rudy. John Pearl was interested in minor planet and moon surfaces. Bob Samuelson was my mentor. And we worked together on finding aerosols and condensates in the atmosphere of Titan. Joe Peraglia was a dynamicist. Gordy Baraka liked trains. Paul Romani, I just spoke to Paul today. Unfortunately, he's leaving Goddard because of the rifts. He's a brilliant photochemist. We're losing a lot of talent. John Prasunas, he supported the project, like a number of planetary projects. I don't think he was as heavily involved as the others. And then Barney Conrath became the Cassini Sears PI after Virgil. So these are just great people that you work with these people for decades, right? And so you become friends, you socialize with them, they're like your second family. Here's the ARIES instrument. I'm going to talk a little bit more about that since that's what I worked with. It's a Michelson type interferometer. So it has light comes into the instrument and is split along two right-angled paths with a beam splitter. Those paths are brought back together. One of them reflects off a moving mirror, so the path length changes, therefore the interference pattern changes. And in order to get data out of that, well, there's the data. This is an interferogram, right? So this is voltage and this is distance as that moving mirror moves. It's just an interference pattern. You can't do anything with it until you apply a Fourier transform to it. And then you get this. This is an actual infrared spectrum of Saturn from Voyager. We measure wavelength in wave numbers, 1/centimeter. This is brightness temperature, but you could construct one with radiances as well. And you can see that we can identify molecules emit in the infrared largely, which are rotational vibrational lines of the molecule. So that's how the ARIES instrument was designed. And so here you can see a little, this is C2H2 acetylene, C2H6, ethane, ammonia, phosphine, and methane. And this is hydrogen in here. Also, what you would see in here if you were able to model it is the aerosols and condensates in the atmospheres, which would be modeled through emission, absorption, and scattering. And so I tended to work more in this area, not in the line-by-line area. We had problems, as many of the instruments on Voyager did. It turns out that this mirror, one of the mirrors in the interferometer, was applied with epoxy that worked great until it got really cold. And when it got cold, it crystallized and it moved the mirror. Therefore, the power spectrum degraded over time, and I had to plot that. It's one of my old plots showing how the power curve was degrading. So the solution to that was just before encounter, turn on the flash off heater, which you don't want if you have an infrared instrument, right? You don't want heat. Wait for things to settle down. That put the epoxy back into solution, increased the power spectrum, and then let it degrade over the course of the encounter period, and that worked pretty well. All right, I promised some pretty pictures, I think. So Voyager at Jupiter, we're out at 5 AU, getting 1/25 as much light per square area as you have at the Earth. And this is one of the pictures, as I mentioned, reassembled in the Earth color picture of Jupiter with some of its moons. This is Io. I'm not sure which one this is. This is either Europa or Ganymede, but that's Io. Just a gorgeous image. By the way, from the narrow angle camera. This is a Voyager film sequence ingress. Let's see. I may need my technical support person again. Why can't I do this?
Because it's too simple.
Because it's too simple. All right.
Simple right here.
So I think I'm switching slides, but I'm in fact, okay, here we go. Thank you, Laurie. This is an assembly of around 100 images of Jupiter as we are coming in before close encounters. You can see, obviously, the Hadley cell type circulation. This Jupiter has 12 kind of what you might call Hadley cells. And this is a direct function of its rotation rate, which is just slightly under 10 hours, right? For a planet as large as that. Let's try this one more time. That's pretty fast. Also, you can see things are moving in different directions. There's tremendous wind shear between the different cells of the atmosphere and, of course, the great red spot. The bright areas are called zones. That's where air is upwelling into cooler areas, and so you have different things precipitating out at those colder temperatures. The dark areas are called belts. That's where air is downwelling into the planet. So you see warmer temperatures with different condensation properties.
Question, what wavelength would that be in?
Well, it's visible.
Visible light, okay.
Yeah, it's visible wavelength. Oh, thanks. I think I'm going to skip this slide. Kind of low resolution. Okay. Here we are looking at the rings of Jupiter. By the way, Jupiter's rings were the only ring system in the solar system to be discovered by spacecraft first. The ring systems around Saturn, Uranus, and Neptune were discovered by the ground, on the ground first, through stellar occultations. And we're seeing some dust. And you're seeing the shakiness of the scan platform here. And you're also seeing some of the ring material. One thing we're able to do with our squiggly lines is develop atmospheric profiles. This is for Jupiter. And this is a thermal profile of the pressure and temperature. So temperature versus height. Well, we don't really say height because Jupiter doesn't have a surface. So we use pressure in millibars. And you can see that there's a troposphere, a tropopause, and a stratosphere as the temperature increases over time to get closer to deep space. This is done with radiative transfer modeling from the infrared data and also the radio science data that we got from the spacecraft. Io, we didn't know anything about Io, not really, but we found out that it's the most volcanically active object in the solar system. And this is more of a real true color image of Io. The surface is covered in kind of yellowish orange material, and this is sulfur compounds that are irradiated with ultraviolet light to give different hues. So this is a direct result of the real tremendous volcanism in the moon, and the volcanism is caused by it's relatively close in its orbit to Jupiter. Io, Europa, Ganymede, Callisto. Io's closest of the 4 Galilean moons, and so it feels tremendous gravitational tug from Jupiter as it goes around in its slightly eccentric orbit, and that produces heat, and that generates the active volcanism. See more evidence. Europa, very interesting. We see striations, which are similar on Earth to, say, water freezing over, and then a crack comes in the ice, and water from beneath comes up and fills it in, and so you get this kind of double-sided crack in the ice. This is evidence, one piece of evidence for a subsurface ocean on Europa. Another piece of evidence is that when you send a spacecraft with a magnetometer by Europa, the magnetometer twitches. And it twitches, we believe, because this ocean of water that we now think is under the ice cap of ice sheet of Europa, potentially more water than all the oceans of the Earth, is saline ocean. And saline water conducts electricity. And as we know from the 1800s, for Michael Faraday, moving charge, moving current generates a magnetic field. So Europa is a high interest target, and we have another mission going to Europa now, don't we? Europa Clipper. Ganymede also has a subsurface ocean further down under thicker ice sheet. The surface doesn't have many craters, and so that means it has been kind of paved over time. This is if you want to be a good planetary scientist. If you have a lot of craters on the surface, it means it's a very old surface. If you don't have many, then it's a fairly young surface. All right, on to Saturn. Saturn is twice the distance from that Jupiter is from the sun, 10 AU, 1% of the sun's light is reaching it versus the Earth. So we're out in the real depths of the outer solar system, cold, icy outer solar system. These are the paths of two Voyager spacecraft into the Saturnian system. It turns out that they all had a ring plane crossing, and there was dust collisions identified by one of the fields and particles instruments on Voyager as it crossed. And the scan platform froze right at ring plane crossing. It was pointed at a target, and when they looked at the image, there's no target. So this was traced actually to a design flaw in the instrument, in the scan platform. So it was in the papers, and I just present that here. I think the next slide might, no, not quite. By sending a series of commands, they were able to free it up, and the decision was made to only run the scan platform in a low velocity movement from there on out through the mission. But it was it was kind of a scary time. If your instrument's on this and it's not pointing, you're not happy. Another interesting thing that we saw at Saturn were these spokes. You guys know about those spokes on the rings of Saturn? Turns out these are, this is dust being electrostatically elevated above the rings. The rings are made of almost entirely water ice. So they're very bright, very reflective. And so if you have dust being elevated above them, it's going to create a shadow. Or at least an absorption. Enceladus, we have some much better pictures today from the Cassini imaging subsystem of Enceladus, which we would recognize as some tiger stripes on the moon. And also Cassini discovered that Enceladus has cryo geysers, right? Water ice spewing. In fact, I had one of those images in here, actually in animation. I thought, wait a minute, Voyager didn't see that. I'm sorry, guys. Invite me back for a Cassini talk. But we now know that Enceladus has a subsurface ocean with cryo volcanoes. And just to cheat a little bit more, Cassini flew through those plumes, collected material, moved it through its mass spectrometer, and found out that, yes, there's a lot of water ice, but there are also a ton of organics in that. Organics. Let me say that again.
How recent was that?
This image here?
Know that they found the organics.
Oh, fairly early on in the mission. Let's see. So it was launched in '97, probably in the early 2000s.
Do they know which organics they found? I mean, is it just like methane, or is it carbon monoxide or something like that?
They do. Of course they do. And I'm sorry, I can't report on, I don't know. Hydrocarbons and nitriles for sure. I'll get back to you on that. Mimas, a smaller moon of Saturn, famous for its large impact crater here, which likely came close to breaking the moon apart. Again, a fairly cratered surface, which means it's a fairly old surface, which means there's probably not a lot of geological activity, if any at all, going on with the moon, which would cause resurfacing. On to Titan. All right, we're still at Saturn. This was the big target, Titan. Back in the 1940s, Gerard Kuiper identified methane in the atmosphere of Titan. And at that point, it became a very interesting object. It's the only moon in the solar system with a significant atmosphere. What you're seeing here is not the surface of Titan. You are seeing the cloud tops. It has a photochemical haze produced by the dissociation from UV light of methane and nitrogen. And so this haze produces these kind of submicron sized particles. We know that from scattering models. And so we're not seeing the surface. But what you can see is a light area and a dark area, right? You might say, well, maybe that's a sun angle. It's not. This is a composition difference. Titan is a very slow rotator. It's tidally locked to Saturn. So it only has, I hesitate to say it this way, but kind of two weather systems, or two what you might call Hadley salts. And every Titan half year, yes, there's a wholesale movement of material from the south to the north, and then half year later from the north to the south. So that's a real compositional difference, as well as probably a particle size difference. You also see a darkening up here. That is real. That is the North Polar hood. And here we are in North Polar winter. And so that part of Titan is shielded because Titan is tilted. And so you're having a buildup of material in the atmosphere that is producing more absorption. Yeah.
Yeah, just, I'm a little confused because,
I am too.
well, year, but obviously the 34 year that Saturn takes around the sun.
29 and a half.
29 and a half, sorry. It's hard to remember all of it. 12 for Jupiter and 20 and a half.
Yeah.
Yeah. But, that obviously should make changes to the Titan.
Well, Titan's tidally locked.
Right.
So which year is Saturn's year?
Okay.
Yeah.
So we're all talking, when you talk about a year, you're talking about Saturn's.
30, roughly 30 Earth years.
Okay.
Yeah.
That's what I was confused.
Yep. Here's a limb image showing the haze layer here. This has been colorized a little for detail. It's a detached haze layer, and it is very similar to Pluto's detached haze layer that James Webb Space Telescope recently took images of. It was in the news. I'm sure you're all watching that. No, okay. But the same radiative transfer models, I think, are appropriate, the ones that we built for Titan, that can be used for Pluto. This haze, by the way, these submicron size haze particles kind of drift down in the atmosphere very slowly, and they become nucleation sites for other gases, nitriles and hydrocarbons to glomp onto. And eventually they get heavy enough and they rain out. And so we knew before Cassini, from this data, from the radiative transfer modeling that we did, that there is a chance, a good chance, that there were at least lakes on Titan. Probably not oceans. Active radar measurements said probably not oceans, but certainly large lakes. So the Cassini-Huygens mission that parachuted down into the atmosphere of Titan was designed to land on hard ground, marsh, or seas. As a result, in part, from this work that we did. We took the ARIES instrument, scanned down from deep space onto the surface of the planet. Here are the infrared spectra that we got from it. You can see there's just an enormous soup of hydrocarbons and nitriles in the atmosphere, often referred to as kind of an Earth prebiotic atmosphere. These are photochemical models. These might have been generated by Paul Romani. I'm not sure. So nitrogen and methane, right? Nitrogen is the dominant species in the atmosphere of Titan. Methane is the dominant volatile in the troposphere down near the surface. And in either event, when ultraviolet light hits those, it breaks it apart and they produce this wild, crazy series of other molecules. Notice HCN. Hydrogen cyanide is in fact one of the building blocks of amino acids. And so Titan all of a sudden becomes very, even more interesting. I mentioned that the radio science subsystem was used as an instrument, and this is called radio occultation. So here we have, this is Cassini. But Voyager did it too. Cassini, I don't know, because it's pretty. It went behind Titan and shot a radio signal through the atmosphere, scanning down. And the more it scanned down, the more refracted the signal became. received at Earth. And again, that signal produces a quantity T over M, temperature over mean molecular weight. We knew that the atmosphere of Titan was largely nitrogen. So that's an N2 would be a mean molecular weight of 28. So now we know that, we know M, so now we can get T, and we can get the temperature profile. Kind of exciting, isn't it? And there it is. And this is kind of the next step in understanding what's going on Titan, understanding seasonal variations, understanding weather systems, rain, methane clouds. Some great debate at Cornell University that we had with Sagan and a group from Canada. Are there methane clouds? And it was yes, no, maybe, I don't know. And it turns out there are. There's methane supersaturation in the atmosphere. Just a beautiful parting image of Saturn. I don't know how I'm doing with time, but probably not great. We're behind Saturn. You can't see this. You take a picture like this from Earth, showing the shadow of Saturn on the rings. Just a beautiful image. On to Uranus. Uranus was one hell of a big disappointment. All the structure and morphology and from Jupiter and Saturn and all the moons, and then we get this. It really was kind of a downer. It turns out though that if you stretch the image using image processing, you can actually see different circulation in the atmosphere. But visually, in broadband visuals, it's not much to look at. So there's the boring image, and there it is with image processing stretched. You might recall that Uranus runs around the solar system like a barrel, right? It's tilted almost precisely, not quite, but almost 90 degrees to the sun. So it kind of rolls around the sun, and that's what we're seeing here. These are just some film sequences of various features in Uranus as they rotate around the planet. Some high altitude cirrus type clouds here. And remember, let's go back to the beginning of the talk. What's the difference? Temperature, dynamics, composition, right? So the colder things are, different things condense out of the atmosphere, right? The bluish color of Uranus and Neptune, by the way, are caused by methane absorption. Methane absorbs in the red. So you take the red away and you have more of a bluish planet.
Are those donut-like things, or those actual, or those artifacts?
Those are atmospheric features, and I'm not really sure what they are. So you can build models here of the temperature profiles, they're called. Temperature here, pressure here is what you think of this as kind of altitude. And I think this was a partnership between the radio science and the infrared spectrometer. So up here where the atmosphere is fairly thin, we had fairly good data for Uranus and Neptune. And then as you go down further and the atmosphere gets more and more opaque, your standard deviation goes up, and you know a little bit less about what's actually going on. And here's some various species here. Ring system of Uranus. These streaks here are stars. I'm sorry, dust, because it's a very long exposure. Now we're out at 20 AU, right? So you're getting 1/400th the amount of sunlight that you would at the Earth. So you have to have very long shutter speeds. And now, but you can image process it and play some games, and you get these very pretty pictures of the structure of the ring system of Uranus. Just Miranda, one of the moons of Uranus. You can see that something doesn't look right here. You got this part of the moon, you got this part of the moon, you got this part of the moon, and just in terms of topography, they look very different. And so some of the thinking is that we may have a moon here that was broken apart and then came back together in some kind of different way. that not quite assembled as it was before it was impacted. The early solar system was a very, very volatile environment. It's just a close-up showing a little better the various surface features. So then we say goodbye to Uranus, behind the planet. A beautiful image of the crescent of Uranus. And on to oh, thank goodness. Atmospheric structure. We're saved. This is the great dark spot. It behaves very similarly to the great red spot in Jupiter. You see high altitude stratospheric clouds. They're white because they're scattering light efficiently, and they will move around this great dark spot in the atmosphere. And again, blue color is from methane absorption. This is how the images came down. I mean, I'm showing you these pretty pictures, right? But this is how this is what you get at JPL before there's all this image processing. And I can't begin to tell you exactly what all the numbers and letters here mean, but this was all of this information is important to the imaging team. Triton, largest moon of Neptune, and what an interesting place. Triton has an atmosphere, not much of one, pretty thin, but technically it has an atmosphere. It also has cryovolcanism. See these dark features here, kind of going more or less in the same direction. Those are that's cryovolcanoes. And they're not coming from a subsurface ocean, they're coming from sublimation of ices just under the surface. Okay. So sublimation means go from solid to a gas, right? So immediately you're expanding greatly. And as the sun hits those areas, the ices just under the surface expand and shoot out maybe 8 to 10 kilometers in height. And then the very tenuous atmosphere of Triton blows it in roughly the same direction. So what an interesting moon. I doubt we'll be getting back to Triton anytime soon. But I would love to see another outer planetary mission.
I heard they're like debating between a mission to Uranus or Neptune. I think Neptune won out.
There's something called the planetary, the decadal survey. Every space and earth science community has one. There's a planetary science one, a heliophysics one, astrophysics, and earth science. The planetary decadal survey, the most recent one, does put a Uranus or Neptune mission near the top of the list for new missions. However, my friends, here we are today. Okay. Fortunately, the Senate and House budget committees are strongly in favor of not only current NASA and NOAA and NIH budgets, but increasing them. This works out great unless there's a continuing resolution, in which case the executive person can take some of that funding when it becomes, then I don't know what happens. But yes, an outer planetary mission is high in the planet on the list from the planetary decadal survey. Just a little higher resolution image of Triton showing its cryovolcanism. What else can we know? Dynamicists can give us wind speeds. That was really weird. Why do we have high winds? Because the sun heats the earth heats the air rises, you get winds, right? Really? Out at 10 AU? 400 kilometer wind speeds? Kilometers per minute? No, sorry, meters per second. We weren't expecting. No one expected that. Beautiful, beautiful farewell image to Neptune. This is August of 1989, the end of the mission. Triton and Neptune. This was planned. This was a planned picture. Just a lovely way to say goodbye to the primary mission of Voyager. Time to party. August 1989. Final planetary encounter. We're out there. There's Chuck Berry doing his thing. He's actually pretty good. Carl was there. Every mission science instrument team was there. Everybody was there, and we partied until we couldn't party. Which for planetary scientists means kind of a double Coke. That's not true. It was an exciting time, just to be a part of this grand story, which was ending for most of us. But in fact, not for everyone. Carl had another idea. Let's take a picture of the solar system from now out past Neptune. So they turned the spacecraft around and they took pictures of all the outer and inner planets. This is a better picture of those pictures. And here's the Earth, a tiny dot in a sunbeam. That's it. And as Carl would say, that's home. That's it. That's everything we've ever known. That's everyone who's ever lived. Every teacher, every warrior, every scientist, every musician, everything we've ever known exists on that tiny dot in a sunbeam. There you are. You're right there. The mission was over for many of the instruments, the imaging subsystem, the infrared spectrometer, ultraviolet spectrometer, the photopolarimeter. Turn them off, right? We have only so much power from the RTGs. But the fields and particles instruments, 5 of them, and I think 4 are working on one spacecraft and all 5 on the other, stayed on. And so we were able to tell when the Voyagers crossed the heliopause into true interstellar space. So here you have the solar wind pushing outward, right? As you move outward from the sun, the density of the solar wind and thus the magnetic field strength and the force that it has diminishes. And at some point, it just matches the pressure from interstellar winds, right? Supernova and that kind of thing. And at that point, at this strong cutoff. This is just a graphic showing the heliosphere. It moves, it pulses based on solar storms and the material through the galaxy that we're moving through. It's believed to be somewhat comet-shaped as a result. This is from, I think this is from the cosmic ray subsystem. October 2011, this is Voyager 1. Here we are in the heliopause. These are experiencing solar wind particles, and then all of a sudden this drop off. At that point, we are in interstellar space for Voyager 1. And here's a nice animation for Voyager 2. Not only do the number of solar wind particles drop off, but galactic cosmic rays increase. 2 strong pieces of evidence that they crossed the boundary into interstellar space. Okay, let's see here. See if I know what I'm doing now. I don't.
Yep, now you can click it.
I thought I read somewhere recently that one of the spacecraft out there hit a place where the temperature increased greatly.
I'm not aware of that. Maybe. I mean, this is from the plasma wave science instrument. Just think for a moment. Just encountering areas of high density plasma in the interstellar medium. So where are Voyagers now? I took this off the screen this morning. Distance from the sun, 15.5 billion miles for Voyager 1, 13 billion for Voyager 2. One-way light time, almost 1 day. Distance from Earth changes, of course, as the Earth goes around the sun. It does go around the sun, by the way. So if you are interested, go to the JPL website. This is actually updating. I couldn't get it to run, but on my slide presentation, but it updates every 10th of a second. You can see the distance increasing and so on. Let's see what I want to do here. All right, so I'm going to leave you with a kind of a video tribute to Voyager from Ed Stone and other Voyager project team members. Just kind of a nice way to end.
We have ignition, and we have liftoff of the Titan Centaur, carrying the first of 2 Voyager spacecraft to extend man's senses farther into the solar system than ever before.
They were launched in 1977. That's a long time ago. We say 41 years, but it's really two generations ago. You can think of what the technology was. Your smartphone has 200,000 times more memory than what the Voyager spacecraft have. And so it's just exciting that we've been able to get it into interstellar space.
We launched 2 Voyager spacecraft. They were basically the same, but they were on different paths. Voyager 2 was the one that was chosen to do the grand tour. That is to fly by Jupiter, and then Saturn, and then Uranus, and then Neptune. And then after 1989, we began what is now called the Voyager interstellar mission. We were on a path we hoped to get to reach interstellar space while we still had power on the spacecraft to transmit the data back. And that's what Voyager 1 did in 2012, and that's now what Voyager 2 is starting to do in 2018. The sun creates this huge bubble of plasma, ionized material, goes outward at 1 million miles per hour and creates a bubble. And inside the bubble, most of the material has come from our sun, and the magnetic field has come from our sun. Outside the bubble, most of the material comes from other stars that exploded 5, 10, 15 million years ago. We have an instrument which measures the wind coming from the sun, and we saw that, in fact, there was no longer any measurable solar wind. We had left the bubble, basically.
The team has been looking forward for this for a long time and really working hard in an engineering sense to make this day happen and to keep the spacecraft with all the instruments on so that they could, all 5 instruments could sense the heliopause crossing and have data for that. What that means is that the Voyager 2 spacecraft is now traveling in interstellar space.
Well, this just contributes to the number of discoveries that Voyager has been making, and this is one we'd hoped we would have the chance to do, and fortunately, the spacecraft were still operating when they reached interstellar space. It's really quite remarkable. Voyager changed our view of the solar system, really. I mean, we saw these active volcanic activity on Io, we saw the possibility of ocean on Europa. Just time after time, we were discovering things that we had not really even imagined some years before the Voyager mission. What makes it so exciting is not only do we confirm what we thought we knew, but even better, it tells us where we didn't know that there was something to be discovered.
And I think we'll stop there, and I'll take questions.
Dr. Mayo, how long were these things designed to operate for? It's been almost half a century.
Well, that's a tough question to answer directly. They were designed to have redundancy. They were designed to be reprogrammable. And they were designed with the RTG in mind, 87-year half-life. So I don't know the absolute answer to that, but certainly well beyond Neptune. So they launched in 77, Neptune encounter was in 89, that's 12 years. So I imagine much longer than that. Yes?
That, well, we mentioned with the epoxy and the mirror,
Mm-hmm.
you said there was a design flaw. Did that impact both Both Voyager 1 and Voyager 2.
I think so, yeah. Yeah, they were essentially identical instruments. Yeah, that,
Is there a dedicated team still monitoring both?
yeah, well. For the time being, there is. Okay. This is how they fixed the flight data system. They had people going through reams of old Fortran manuals and old printouts. I mean, decades old, and assembler language, and they figured out how to reprogram the onboard FDS, and they did.
How many people alive are capable of that?
Fewer and fewer.
Well, I'm still a Fortran proponent, so should say that much. Yes, sir.
So they're beyond the Kuiper belts now?
No,
They're still in the Kuiper belt?
Yeah.
But inside the bubble,
outside the bubble,
outside,
outside the heliosphere. Yeah. In true interstellar space.
and instruments, some instruments are still running?
Yeah, I don't remember which one it is. There are 4 fields and particles instruments on one of them and 5 on the other that are running, and they're cycling these instruments on and off to try to save enough power to be alive in case their funding allows for operation through 2027. To have a big 50th anniversary celebration.
So from in the aggregate cost benefit analysis, they're probably the best bang for the buck we've ever had.
I think so.
Yeah.
I think so. Now, I should mention that most missions that we design today outlive their planned lifetime. It's not unusual to ask for extended funding. And even for Cassini, for example, they asked for 2 extended funding periods. So, but Voyager, I think, is exceptional. Other questions? Yeah.
Oh, I cheated. While you're talking, I checked an AI source.
Mhm.
It turned out that according to that there was each spacecraft had a ceramic stylus on them. The only controversy is who made it. The company that got credit is, I guess they were no longer making them at that time.
Whatever a stylus is, yeah.
It's not gonna be the only fingernail record.
Yeah.
How much data sharing are we doing with like the Chinese and the Russians, if any?
Well, all the data is public domain.
Most of it's published, right?
Yes.
It's not a secret what frequency.
This is data, these are images and other data that you've already paid for. So it belongs to the public. So it's out there. Now, we don't generally partner with the Chinese. This is a government decision when we're building new missions, but the data is public domain. Any other questions?
Yeah, why did they change Mary Washington to Marymount? As far as the name? It used to be Mary Washington.
Oh, I have no idea. That's before my time and above my pay grade. Yes, ma'am. Yes.
I was curious if you knew what was driving those high wind speeds.
Well, I mean, even though you're far from the sun, you do have energy sources. There is the sun, of course. You can have absorption of solar radiation from aerosols, for example, and from other gases, producing, condensation and this kind of thing. You also have heat coming from the planets themselves. There's a positive heat balance, at least for Jupiter and Saturn. I think perhaps for all 4 gas giants. So you have that heat source as well. And so there is movement, there is energy to convect the atmosphere. It's just not what we're used to.
And the fact that Jupiter's 10 times bigger and rotates a whole lot faster.
Yeah. I mean, it's really incredible.
Dragging the wind around, maybe if nothing else.
That's why for amateur astronomers, you can't keep your shutter open if you're imaging Jupiter for more than 90 seconds, I think, because it's rotating. You get a smear in your image. And then there's software to derotate your pictures, but 90 seconds, I believe, is about the max. Other questions?
What was your impression of Carl Sagan as a person?
Stunning. I remember the first time I met Carl, we were working on the same problems in planetary science, methane clouds and methane supersaturation in the atmosphere of Titan. And so I knew Carl, I knew his work, he knew our work, and there we are at JPL, right? And he's always got a crowd around him, always. And so I don't know how to approach him. Do I approach him as a superstar or as a colleague? Hard to know, and of course, he always has a crowd around him. Well, he was about ready to leave. We're out at JPL for one of the planetary encounters, I don't remember which one. And he's walking up the stairs, probably thankful to get away from all the everybody. And I said, here's my chance. So I said, Dr. Sagan, hi, he turned around. Lou Mayo, working with Bob Samuelson on the methane cloud situation. And he put his hand on my shoulder and looked right in my eyes and said, Lou, of course, so nice to meet you. And he turned around and left. He did, and I was stunned. He just had that charisma. Another time, he had just given his kind of his swan song, the past, present, and future of planetary science at a Division for Planetary Sciences conference in Hawaii. And so I was at the airport, it's an open air airport, and he comes in, and I thought, well, it's a great chance to talk to him about our Titan research. So I said, do you have time to talk about Titan? And he said, I always have time to talk about Titan. And so he ushered his family into the cafeteria and came, and we had a nice half-hour chat about our research. He's a lovely guy. Yeah.
All right, well, thank you.
So we have something for you, but we're not sure where in the room it is.
Do I have to feed it?
Oh, it's over.
Yeah.
Oh,
Oh.
Yes, we were sort of very thankful that you came.
Thank you very much.
And if you want to stick around for the rest of the meeting, you can, but you're free to go.
Oh, I'd love to. Thank you.
Thanks.
Thank you.
Shall I open
okay.
Well, I think there's a patch in there.
Time for break.
Yes, we're going to take a 10-minute break.
Good.